So we just finished talking about Raoult's law, which deals with volatile solutes. So we went over the examples of chloroform mixing with acetone. We talked about ammonia and ethanol in the last problem. But what do we do about non-volatile solutes? So this still has to do with colligative properties, and colligative properties has to do with the number of moles that we have of a given compound. So what happens when we add non-volatile salts? So I think of adding salt to water before I boil my pasta, my spaghetti, as a good example. Why do we salt our water before cooking pasta? Maybe you just want the salty flavor to be in there, but somewhere along the way, this information has been passed down that your pasta will cook faster. And this has to do with the impact that the salt has on the vapor pressure of the solution. So let's think about this. If we look at the vapor pressure of a solution of salt water, we know that it has to do with the mole fraction of water times the vapor pressure of water. Okay, and the reason we set that equal to the vapor pressure of the solution is because the solution has the water and the salt. Okay, so if we have pure water, then we would have exactly a mole fraction of 1. So it would be the number of moles of water over the number of moles total, which is also 1, right? So they would be equal, and you would have 1 times the vapor pressure of water. Simple enough. So if we add salts, a non-volatile solute, then we don't really have any vapor pressure to add because the non-volatile solute can't go into the gas phase. So what is actually changing in terms of the vapor pressure of the solution? It comes back to that mole fraction. So if we look at the mole fraction of water, when we add some salt to the water, then the number of moles of water is still the same as it was with pure water, but now our total number of moles that are actually in that pot, it has increased because we have the moles of water and the moles of salt. So in effect, your mole fraction of water goes down. Okay, so now we have a smaller value for the mole fraction of water. Vapor pressure of water is still the same, but for the solution, the vapor pressure is lowered. Okay, so that may be a little bit confusing. You might be thinking, okay, so the vapor pressure is lower. Why would my pasta cook faster? So here's the deal. If your vapor pressure is lower, and you can imagine that vapor pressure is pushing down on the surface of the water, but for the water to boil, it has to push the atmosphere out of the way. So remember, there's a lid above the boiling water, which is the atmosphere. And the pressure of the solution has to kick the atmosphere out of the way. So that means that we need to increase the vapor pressure somehow to match atmospheric pressure to reach that. And what that means is that you're going to boil at a higher temperature. So the temperature increases. So in effect, you are boiling your spaghetti at a higher temperature. Okay, so let's go over that for a second. So non-volatile solutes don't exert their own pressure. Okay, so that's why, unlike the previous examples, in Raoult's law, we had the pressure of the solution equals the mole fraction of a solute that's volatile times its vapor pressure plus the mole fraction of the solvent times its vapor pressure. But with a non-volatile solute, a solid ionic compound, it's not going to exert its own pressure. So you don't include it in Raoult's expression. But we have increased the total number of moles that are dissolved in the solution. So your mole fraction for the water goes down. Since there is less vapor pressure from the solution, you need more heat now to make the water boil and kick the atmosphere out of the way, overcoming the atmospheric pressure. So the big takeaway from this is that the presence of solute particles lowers the vapor pressure of the seawater solution or the saltwater solution in your pot for boiling pasta. So this also is a good segue into understanding phase changes for water, and specifically two colligative properties that are related: boiling point elevation and freezing point depression. So again, these are colligative properties. They have to do with the total number of moles. So let's look at pure water first. So this is what we call a phase diagram, and it relates pressure on the y-axis to temperature on the x-axis. And we have the three phases at these different pressures and temperatures. And that makes sense because when you have low temperature, you're going to be in the solid phase. Higher temperatures take us to the liquid phase, and then even higher temperatures take us to the gas phase. So the order is SLG, or slug, is a cute little way for me to remember it. So when we look at these different curves, these are going to be our phase equilibrium curves. So that means that anywhere on these curves, you've got two phases, or here you have three phases that exist at the same time in equilibrium at that given pressure and temperature value. Okay, so all along this curve, we are in equilibrium with the liquid and gas phase, and then we hit 1 atmosphere of pressure. And what do we know about water at 1 atmosphere of pressure? We know that it boils. So this is where we would reach 100 degrees Celsius and go completely into the gas phase. Okay, so that's the case for pure water here. Now, we just talked about what effect adding non-volatile solutes has on the vapor pressure of a solution. So if I add salt to my water, I now have an aqueous solution. So that's going to be this red curve now. What happens when we add the salt is that the vapor pressure drops, and we're now sitting here. Okay? When we're sitting here, we're not overcoming atmospheric pressure, so we can't go completely into the gas phase. We can't boil here. And so we have to increase our temperature because the whole curve has shifted down. We have to increase our temperature to meet atmospheric pressure. So it's exactly what we just talked about in the previous slide, but showing you in a phase diagram. This effect is known as boiling point elevation. Okay, so boiling point elevation on one hand, and then we have an equation that lets you calculate what that change in temperature actually is. And it depends on a few things. One is going to be the boiling point elevation constant. So for water, it's 0.52 degrees Celsius per molal. And we'll talk about molal as a unit in the next slide, or in the next two slides. And the Van 't Hoff factor, so if I'm adding sodium chloride, the Van 't Hoff factor is a little bit less than 2. And then the molality of the solution. So that's going to be a way that we talk about the concentration. So on the flip side, we have a freezing point depression. Okay, so, and that's important to remember. When we calculate the change in temperature for boiling point elevation, you need to add that temperature value to the normal boiling point. When you calculate the change in temperature for freezing point depression, you need to subtract because it's going to be a depression or lowering of temperature. So they kind of go in opposite directions. So the freezing point we know for pure water, and so this is our pure water curve now, equilibrium curve, where we have solid and liquid in equilibrium with each other. At 1 atmosphere of pressure, this is happening at 0 degrees Celsius. But if we have solute, non-volatile solute, mixed in with the water molecules, they don't crystallize as easily. Okay, and so it's important to think about that structure of solids. And solids are very organized. You can think of them as arranging molecules and atoms into cubic arrangements. And so if you start throwing in sodium ions and chloride ions, it's going to become difficult for water to organize itself in that way if there's still some amount of motion also going on. So we have to go colder. We have to make the solution even colder so those water molecules can't dance around at all. And the sodium and chloride will also arrange themselves into that crystal structure. So freezing point depression is when solutions freeze at a lower temperature than their pure solvents. They need to get colder to let them organize into the solid state. Again, we can calculate that actual temperature change, the depression, the value that it's going to go down by looking at the freezing point depression constant for water times the Van 't Hoff factor, which has to do with the actual number of moles of solute dissolved, and the molality. So let's go ahead and talk about molality. So you guys know molarity from before. Molarity is simply moles per liter. But molality is another way to talk about concentration, and it's a more robust way to talk about concentration because it's not affected as easily by temperature. So let's just write down molarity so we can remember that. So when we've talked about molarity in the past, it's just, and that should be a Y, moles of solute over liters of solution. Okay, so one distinction that we have now between molality and molarity is the fact that when we're talking about molality, it's moles of solute still, but we have mass of solvent. Okay, and the mass of solvent is going to be in the unit of kilograms to get to molality. So how do we get to molality? Well, you may have the mass of the solute that you're adding, so that's going to be in grams. Okay, you divide it by the molar mass, so it would be divide by grams per mole. And so you get moles of your solute here. How do we get mass of solvent? There's a couple of ways. You may know the volume of your solvent, so that would be in liters, and you multiply it by the density, which would be in some mass over volume unit, so grams per liter, and that would, you could convert that over into kilograms. The other way you might be able to get the mass of the solvent is starting all the way from the volume of your solution. So you would have the whole solution in some unit of volume, multiply that times its density, so grams per liter, which would give you the mass of your solution, but that's, and you convert that to kilograms, but that's factoring in both the solvent and the solute, so we would have to subtract from that mass of solution the actual solute that you added, which we know from up at the top, and then you would get the mass of your solution that's just from the solvent. Okay, so a few different ways that you could get to that value. So whenever we're talking about molality, remember it's moles of solute over mass of solvent in kilograms. So we're talking about moles over kilograms. And that is a unit that's known as the molal, and it's written as a lowercase m. Okay, so looking back at our equations for calculating these two colligative properties, boiling point elevation is going to be a temperature change from the normal boiling point of a pure solvent, and that's going to be equal to the boiling point elevation constant times the Van 't Hoff factor for that solution times the molality of that solution. Likewise, or on the flip side, freezing point depression is that change in temperature, that's the change that it goes down from the normal freezing point of the pure solvent. And so that's equal to the freezing point depression constant of the solvent times the Van 't Hoff factor times molality. So you guys have to use that lowercase m and get molality in these calculations. All right, so this is the next poll everywhere question. So go ahead and pause the presentation so that you can work through this problem. So if 4.27 grams of sucrose are dissolved in 15.2 grams of water, what will be the boiling point of the resulting solution? Remembering that we're looking for our boiling point elevation value. So the change is equal to that boiling point elevation constant for water, which is provided here, times the Van 't Hoff factor, and it's okay to use the theoretical in this calculation, times the molality. So press pause and answer this question. Okay, so once you've finished answering this question, move on to the very last type of solution that we're going to discuss in this chapter, and that has to do with gases that are sparingly soluble, which means they're not very soluble, but how they dissolve in liquids and what that concentration is. So a good example of this is what happens in the lungs as we breathe in air and how oxygen is actually transported into the aqueous medium of our blood. And this doesn't really have to deal with how it attaches to hemoglobin, but simply how it passes into the actual liquid environment of the blood. So when we look at the concentration of a gas, the maximum solubility it has in a particular solvent, we use Henry's law constant, Kh, and the partial pressure of that gas. So if we're thinking about oxygen, for example, it has a certain partial pressure in the atmosphere, which has to do with how concentrated it is in the atmosphere. And that times Henry's law constant will tell you exactly the concentration that would dissolve into the liquid medium. So just to review kind of what that looks like, the partial pressure of a gas. So if you remember when we talked about partial pressures before, and if we're using the example of oxygen, so we have the partial pressure of oxygen, and it's going to be equal to its mole fraction, okay, and that's going to be how many moles of oxygen there are in the atmosphere over the total moles in the atmosphere. So that is multiplied by the pressure of the atmosphere at that certain elevation, and we get the partial pressure of oxygen from that. And this goes back to Dalton's law of partial pressures. So that is what we're going to plug in to Henry's equation so that you can figure out the actual concentration of the gas. So a pretty straightforward concept, but it gives you an actual value in molarity of that gas. All right, this brings us to the very last pull everywhere question and the last slide of chapter 11. What is the solubility of carbon dioxide in water at an atmospheric pressure of 0.360 atm? Using Henry's law, we have concentration of gas equals the gas constant times the partial pressure of the gas. And these are the different Henry's constants for different gases. So we're looking at carbon dioxide, and you have its mole fraction. So remember, mole fraction is going to be your X value. Okay, so go ahead and press pause and answer this question. And that concludes the end of Unit 1. So chapters 10 and 11 are complete.